Hello everyone, I'm really excited to bring you this conversation about high-performance computing with Xavier Besseron. I met Xavier during my PhD, and he was in charge of pulling the contribution of a squad of researchers like me into a coherent code base. He is the man that introduced me to continuous integration and delivery, and I'm excited to explore with him how modern technology, HPC, and generative AI are changing the way researchers and professionals approach programming. We talk about how we see the intersection between HPC and generative AI, and how his research on complex code profiling is trying to solve some hard problems of computer science. Xavier, thanks a lot for being part of this and having this talk to me today. You have a really cool computational profile, especially very much specialized in high performance computing. You got your PhD from Grenoble and then had a postdoc in the United States and then joined Luxembourg, where you're now a permanent researcher doing incredible things for the future of European computing. So thanks a lot for being here and being part of this podcast. And I would like to start immediately with a very tough question that is. HPC is probably one of the most advanced in terms of fields in terms of complexity when one talks about computer. What fascinated you about it, and what brought you there?
Okay, first, thanks for inviting me. It's very nice, and thanks for listening to me for the next half an hour. That's gonna be fun. So HPC and supercomputers. What fascinated me about that? Actually, I was from the beginning fascinated by computers themselves. So
Mm-hmm.
uh, kind of young, let's say around when I was a teenager, like 14, I had some computer at home, and there was a time before internet, and just playing the little games I had on the computer. But one day I had a friend who had a programming book for computer with a QBasic, the most basic programming language you can find. And
QBasic.
when I saw this book, I looked at it, I read it, I borrowed it to to study it, and then I realized, oh, but with that I can tell the computer to do what I want to do, and I realized I was in control of the computer and
Uh-huh.
doing what the computer allowed me to do. And then I really enjoy programming from that, and I spend a lot of time in a dark room playing with my computer, programming instead of
Out of a
of
manual,
fun
right?
to do. Yeah, you can
Yeah.
see the life of a nerd or something like that. But slowly, I build my path towards computer science and then high performance computing. And high performance computing, in the end, is the same thing, just harder and more complex.
More
You do the
complicated.
same thing, you do programming, but you have more troubles because it's like you have many computers running at the same time, and you need them to talk to each other and to talk
Yeah.
to each other in a correct way.
And doing hard things is something that never scared you. I know it since I met you because I met you as when I was a PhD student and you were a postdoc in the same team. And your task when I joined was taking the work of crazy PhD students that had, let's say, a non-professional experience with programming, so people who programmed but never programmed in a team, and try to make them work together to produce some sort of a product that then could work while they will keep doing the PhD. So now that I work way more on professional software development, I appreciate how hard this kind of task is, because especially when you have very curious people and very creative people that try to change everything all the time, making many of them work together is really a challenge. And I think you were continuous integration and development heroes. And I have to admit, I always appreciated your job, but after I left university, I appreciated your job even more. And this is basically you managed to keep some code quality in what we were doing it with people that never heard about continuous development before. And what I wanted to ask you is actually, what are your thoughts about code quality and code performances, especially when we look at code that is built to run in parallel. So can you tell maybe also our audience what is code quality for you, and also what does the running it in parallel change the equation of how to write good code?
Okay. Yeah. So code quality, actually, this talks also to me a lot, because one part of my study, actually, I studied for as a software engineer. So this covers a lot of things, but basically how to design a software properly, but how to test it, and of course it comes with all this continuous integration. Joining the team where you and many other, let's say, engineers coming with a completely different background was very challenging, as you say, to integrate and to put the work of everybody's together and keep it working. That was the hard part. Let's
Yeah.
say keep the thing working despite everybody coming. But for me, that was very interesting, and I learned a lot, especially in terms of debugging, because of course you are, like, I think at the largest we were probably 15, 20 people putting code all the time, at
Yeah,
the same
and
time.
while doing a PhD, while having the pressure of I have to publish a paper, so I have to make these things work because I need the results. Right? It's not just software developers that okay, you give them a task and it takes their time to do that. They really had this other pressure on churning code, and then you had to make it work. Yeah.
Yeah, it's like I got requests from the different member of the team, but in the end, when you put that together with HPC, so software engineering and code quality with HPC, it's exactly what I explained together. It's the same problem, just even harder, because when you run a program in parallel on a supercomputer, the bug, they will happen, let's say they have more chance to happen because you have the same copy of the program running on 100, 1000 of cores. But also you have some other type of bugs that are specific to parallel execution, like race condition and things like that. And those kind of bugs are, of course, difficult to reproduce. So in some way, working in high performance computing pushes you to improve your code quality, because if you don't do that, just the bugs, they show up more often, and you cannot proceed. On
It
the
will
other
never work.
side,
I remember one thing you told me at the very beginning, that having an HPC is like having a Ferrari as a car. If you don't know when or where you want to go, sorry, it's just gonna make you crash faster than a normal car. It's not gonna solve your problems if the algorithm is not good. Yeah, HPC is not the solution.
exactly, and the naive approach actually with HPC is that, let's say you have a program that is not very fast, that is using a lot of memory, and you can just think, oh, yeah, I have a memory leak. I need a lot of memory to run my program, so I will just put in HPC. I have this machine with big memory, 1 TB of RAM. I will just run it there. I don't have any issue with the memory leak. And this is kind of the wrong approach. It's like, okay, I'm late for my appointment, but I will drive a Ferrari because I will be there faster. And yeah, that's the best way to crash. And
Indeed,
same
indeed.
for HPC.
And I think this is something that out of the HPC domain, we are seeing more and more even with our mobile devices, so both laptops and actually phones, that as phones get more and more memories and laptops get more and more memories, you see apps developed that are worse and worse because they know that they can use 8 GB of RAM without problem because everybody has it. And so they don't really take the time to optimize it. And somehow time ago, apps were actually written in a smarter way. Don't you think?
Definitely, and if we can think at the computers from 20 years ago, 30 years ago, I mean, as memory, they had like less than 1 MB, so, and you could still do things, okay, less powerful than now, but you could still you
You
could
can
still
still put
do
the men on the moon, right? That's as they also say. Yeah.
exactly.
And that's what. And I want to also shift to one argument that is very much in vogue. So you're very much a guy that is very attentive to vogue and style and trends. But it is about generative AI and the impact that is having on coding. So I think that the last 2 years, more or less, were this great explosion of attention on large language models and generative AI in general. And I think that coding is one of the area in which they already are, let's say, mature enough as technology, even though they are, well, personal opinion, but being pushed a little bit too much in any field. I think coding is something in which they are a little bit the readiest of overall. And I really see them changing the way people are coding and changing even what coding is. It's, I think, a shift that is almost similar to the shift between the assembly language and actually higher languages. These co-piloting tools for coding are really giving ability of almost coding natural language, even though it's not really like that. But to me, as personally, is impressive. What's your take about it? Like, do you think they are a overall good thing, a neutral thing? Do you see code quality getting better, worse? Do you have any take on it?
Um, it's very hard question to answer. I think it's the, let's say, those tools are still a bit young to have a definite opinion about it. And myself, I experimented a bit with it, but not too much. What I see is that sometimes I'm actually quite impressed to see like the suggestion, which are almost what I wanted to write, or sometimes just give new ideas. But I think it should be used as a tool and not to replace a programmer, because I've also seen many examples where the suggestion actually is completely useless or
Yeah.
completely wrong, and yeah, some kind of weird bugs. And here I'm, what I'm saying, I think it's very, very general. But I think this morning I read a study that has been published where they were talking about generative AI for programmers, and I think they were saying like it was not speeding up the development, and in the end they were producing more bugs actually in
Yeah,
the
yeah.
final result. I
To
don't know if you
me,
saw this study, but
I don't think I saw the specific study, but to me, as a general take, I think they are very similar to HPC in the sense of the Ferrari approach, right? So they give you a faster engine to your car that is developing a code, but this faster engine can also bring you faster in places you really don't want to go. And I think not enough attention is given into train people on how to use those tools properly. They're powerful tools, almost like an HPC is, even though HPC is just running the computation with more resources or making more resources available to your computations, while this is really developing the code itself. But I think there is a parallel there in the way that they could really speed the development up a lot. I take an example of me. I was never a very good front end guy, right? And with the addition of some large language model, I can now program front end way better because it's something I was lacking before. But they can really super a lot, and things that would have taken me 1 month, I could do that literally in one day right now. At the same time, if I wouldn't know how the overall backend structure works and how the logic of the front end works, after two types, I would have already gone in the direction I would have liked to go. Right. So it's something that, to me, people should learn how to program almost without those
yeah.
tools, and then use these tools to enhance themselves. Maybe it's a little bit of an old guy scenario, but definitely these tools are give you the very, let's say, tempting feature of I don't really need to understand because in the end it runs. But after a couple of iterations of that one, your program is already not doing anymore what you do that, and becomes a nightmare to debug. But at the same time, if you use it in the right place, yeah, like HPC or a Ferrari,
Yeah.
it could bring you where you want very, very fast. No?
Yeah, and as you say, I think probably there should be some training to tell you how to use this, let's say, copilot to name it, like to use it in the right way, or to guide it to really build the answer you want. And
Yeah,
but
indeed.
yeah, in the end, I think you should be able to understand and verify yourself that the code you have written is correct. And this is one of the things I'd learned at the university, is basically to kind of prove that my code is correct. So sometimes it's just checking very, very little thing, checking invariants in the code, and that teaches you to basically, like, if you write an if statement, make sure that to verify what's happening in the else case. And those are very like little thing, but when you do that, you really improve the quality of your code.
Indeed.
Of course, you can do that with code coverage tools and things like that. But anyway, I think that's a good habit to have when you
Yeah, I think it's a great point, and probably the task of the, as you said, they're not really there to replace a programmer, because if you give, let's say, this tool to somebody that doesn't know how to program, likely you're not going to get very far in your project. The beginning will look perfect, but then it will not scale very, very well. But it will make even more important as a skill of a developer the being good at pull requests, because a big part of this pull request will actually be written by an AI, so understanding it is important, and also be good at about testing, right? Because the faster you develop code, the more you should test that code, right? And
yeah.
as I say, with code.
I don't know if you know any tools that will actually, like, maybe AI based tools that will let's say check the code and look at the code that has been written and put some comments. I mean, I know there are some non-AI tools for that, but something that say, okay, here
Yeah. I mean,
maybe something
that's
is
something
wrong,
that,
here you forgot that, and I would put
yeah,
the
no,
two
that's
AI
something you
tools
can do.
compete with each other.
No, indeed, there's something that you can do quite easily, and there are very many agentic-based models that are built on the stack of large language model for coding that do exactly that. So, for example, do better comments on the code. Of course, you have to then read what the machine wrote and
Yeah.
double check that it's actually correct. But also testing. I mean, having is a very basic statement on one of these or any of these tools could do nowadays, as far as I know. Is okay, have this function, read me a proper test for this one, and check me some edge cases on this. They work pretty well for that one, and for that one, to me, is what people should do, because those are normally the boring stuff of the programming, like writing your test and writing your comments, and they really take this all boring part out of it. Of course, you need to check them, because you cannot just trust that any test written is correct or any comment written is correct, but they could point in better software quality in some sense. Yeah. And
Yeah, maybe, and to continue just on this topic of generative AI for coding, in the end, what is the limiting factor for me when I'm programming is
mhm.
not actually the time I spend, let's say, writing the code. It's I spend a lot of time thinking, trying to find out what is the best algorithm, what is how I should structure my data, where I put my data in my object, if I use an array, like array of structure of array, and this kind of thing. And I think this goes a bit, at least for now, this is a bit beyond that what generative AI here is proposing. So I think in the end, this does not, speed up too much the development of a code, at least for my experience. But I hope this will change, and then
So
I will be able
I
to use
cannot
that to.
believe it, because normally I'm the one critical about the generative AI, so I will be the one defending it in this conversation. So that makes the richness of the conversation. I actually think that. One other thing that is pretty good in some of these tools is that it could help thinking about stuff. I mean, I think this is a great feature that is in general of large language model, not just for programming, but of all their tasks, that they can act as a sparring partner when you don't want to bother your office mate with should I use an array or should I use a array,
Yeah.
but you can have this conversation that is not really they are going to give you the best answer, but it's more like they make you in the mindset in which you can talk, because you're just discussing with a peer, right? And that, at least for me, many times is just what I need to do, like say my things out loud or write it the things out loud, and then
Okay.
have
Yeah.
this process, and then okay, that's what I should do. So I will defend it on this one. But I also wanted to ask you, just in case you have it, I know that these tools are particularly used for certain amount for certain type of programming languages. I program a lot in Python, and for that one are quite great because there are a lot of let's say Python is one of the main languages these tools were well trained on. But I know that there are other, let's say, programming languages that are a bit more niche that maybe those programming languages are not that fluent with. So this large language model are not so fluent with. Regarding specifically on HPC, so on this kind of technological stack that is let's run these instructions so that they can be efficiently run on multiple threads. Do you know if there are any specialized large language models or tools to make this very complex subject a little bit more approachable also for people that maybe never heard about HPC?
Mm.
Or rephrasing it, have you ever tried to use ChatGPT to understand how to run Slurm statements properly?
Okay, I remember, yeah, doing that. That was more like, at the beginning of ChatGPT, trying to see how good it is to, yeah, to ask question about Slurm. Okay, how can I do that with Slurm, thing like that? And yes,
They're
I
pretty
think
good.
it works well because there is a good documentation on Slurm which covers pages and pages. So I think it has been able to learn from that. There are many examples. Now I've not really used that in practice, and to be honest with you, I have a lot of Slurm scripts that I keep reusing all the time. So now those things work. I don't touch.
It comes so natural for you that you don't want to write the program in a different language and have somebody translate it for you. Yeah.
Almost.
So there are those memes about I'm fluent in C++, no, you're fluent in Slurm. That, by the way, is a language focused on load balancing, balancing the load between the different agent in an HPC. So very niche thing for anybody who will get. Okay, cool. And a little bit broader horizon. Like, can you tell me a bit what's currently your research focus on, or what's something in the field of research that you touched that is exciting you particularly? Because it's quite sometimes we don't interact on a research level. I mean, we wrote a proposal once together, but yeah.
So I think, you remember when we worked together, we were working on this multi-physics software, XDM. And now I'm trying to look a bit around. So it's still connected topics. And now I have kind of two topics I'm really interested in. One is about software verification. And basically the idea is that you will be porting a software to a different, let's say, programming language, or for a different type of processor. Let's imagine you have a code on CPU and you port it to a GPU or even a FPGA if you want to have a lot of fun. And the question, okay, is the result is correct? Is the new program is correct? And can I compare the result of the new implementation to the old one? And the short answer is no. I mean, you should not expect to have exactly the same result, and that makes kind of testing and verification in that case very difficult. So I'm looking in some ways. I mean, first thing is to assess what kind of difference, and if they are big, if they accumulate, if they grow with the time. So first thing to assess, and thinking at some tools that will, let's say, ease this comparison. The idea is to do verification across architecture, but still be able to do it despite of some numerical differences. So this is one first topic.
Yeah. I remember like the first time I was exposed to parallel computing was even before meeting you. So it was actually during my master's thesis that we were running a CFD simulation. So trying to resolve PDEs related to fluid flows on a mesh, and it was, let's say, the code was working perfectly in sequential, so when you run it on a single processor. And then I remember that I had a very mathematical approach to this kind of problem. Like we are trying to find a unique solution to our physics and equation. And then we run it in parallel. We got a slightly different solution, of course, to the decimal side. And I remember my professor saying, yeah, this is normal. In parallel, it's different. To say, what? We are looking at a single solution. And I had all of these things. This is normal. And this was the first time that I said, okay. So things tend to be more complicated because in everything that is numeric, you have this numerical error that will change quite a lot when you scatter, like say, computation and then regather it. And so you can have side effects that are quite pronounced in a software, especially when it's very delicate, right? So something like PDE's solutions of nonlinear equations.
Where they get the little error get amplified.
Exactly. And this makes it very challenging to write good tests for this software, right? Because depending on the number of processes and similar, you cannot check exactly that you get the same solution out of it, right? It needs to be a band that is makes sure that this error, so this difference, is purely related to the fact that you use this architecture and this part. So I can imagine being very, very complex to write good testing for that.
Yeah. So the other topic of research I'm working on right now is a bit at the corner of let's say numerical simulation on a high performance computing platform. Machine learning, and the idea is and performance modeling. So the idea is that when you have a program, an application running in parallel, it is very important to use all the CPUs efficiently to do a proper load balancing. So to distribute your work in a nice way across the processors. And for that, we have tools to do that. They are called partitioner, for example. There are many others, but that basically, you give a list of tasks, you assign a computational load to them, and you say, okay, distribute, it gives something, you distribute. It works well. It works well only if the estimation you have made of the computing task is correct. And if you're not able to estimate the load associated to a task, if you cannot give a good estimation, then of course the load balancing you will get in the end will not be very good. So here I'm trying to do some performance modeling to learn using some machine learning algorithm to learn the computing load on some computing task. And here I'm looking at computing tasks, of course, that are difficult to predict in terms of load. And if you remember our code with discrete element method, you will have, for example, a computing load that will depend if particles are in contact. Because if they are in contact, you will have to process some impact model, some rolling model, and things like that. But if they don't touch, then you don't have to process that. So that impacts the computing load. And this is just a very little difference in the positions that can do a contact or non-contact. If you want to talk about CFD, you can look at reacting flows, and in reacting flows, you will have some chemical reaction, and some reaction will take place only if we are at a certain temperature. And so that will impact the computing load of some computing tasks. So of course, you could study things carefully and try to make some to have some good estimation for the load of such computing tasks. But here the idea would be to do it using machine learning. And of course, I want to go a bit beyond, like instead of measuring, let's say, the computing load of each task individually, I want to learn, but just by looking at the global picture. I don't want to go and measure. For my training, I need to collect data. So I don't want to measure the task individually, but I will try to measure the load at the level of a process, and from that be able to deduce and learn the pattern of the computing task individually.
Yeah,
so
super interesting.
This is work in progress, of course, and I hope this will give some good results.
Yeah, no, that's super interesting, because I was briefly exposed to that one towards the end of my PhD with actually worker where we collaborated together, and it was really focused on, we have a new let's say numerical method to study specific kind of flows, right? And I was trying to use the fact that I knew something of the physics of that problem to have a routine on how to parallelize this coupling between the code that was running the fluid and the code that was running the particles. And the idea is, if you know the physics, then you also know a little bit of the kind of information that these things have to exchange, and so you can optimize it. So very specific optimization for one case. And on the other side, after I moved more into the data domain and to the let's say industrial domain, you see this other big trend in virtualization technologies, let's say on the Kubernetes side, that try to completely abstract out of the machine and out of the problem and load balance in the best way by being almost completely problem agnostic. With problem agnostic, I mean I run in the same way if I'm running a simulation or if I'm running a data packaging and data stream. And I think your research, if I understood, is a little bit in the middle, like trying to understand on one side that each problem is specific and trying to infer how can I optimize this, but at the same time trying to be generic enough, like maybe not as Kubernetes as a kind of container orchestration technology, but still going the generic part. I don't need to know the physics before I start thinking about it in parallel, right?
Exactly, yeah. It's about, in the end, finding the right level of abstraction. So you build a model of your application. The goal is to build a performance model, but before building this performance model, we build the model of the computation, and in that case, it's about small computing tasks. But for sure, we know that it depends on some information that are domain specific, like local temperature in the CFD cell or position of some particle. And this, we try to extract only what is necessary, but be able to learn in a generic way independently of the specific application.
That sounds really exciting.
Yeah, and focusing on a category of application, because of course we cannot address everything with one method.
Yeah. There is always space for something in between. Like I don't think it makes a lot of sense to reinvent Kubernetes from scratch or to be hyper specific on the other side, and there is still space in the middle. One last question is, in general, now if you abstract even more, right, and you just look at HPC really in general, not necessarily related to your research, what are the big trends that you are keeping an eye on, or did you find interesting in the last year or in the last 3 years?
As I think one of the big trends you've heard about it is AI, because that's what we hear all about recently, and actually that's a major trend, specifically related to HPC, because what I've seen in the last year is that let's say AI has been democratized, and with all this deep learning framework. And we see now very quickly people being able to use HPC at full scale or with, let's say, very large application, and coming like that very quickly, making a relatively good use of a HPC platform. So in some way, yes, this is a kind of democratization of HPC in that sense, like, yeah, people are able to use HPC without too much let's say knowledge about the specificity, which is like, it's almost like yeah, people they manage to, let's say, they improve the wheel on the driving wheel on the Ferrari, and people are able to drive it better. I think for that the good what makes this big change is that actually, if you look at the deep learning framework, let's say like TensorFlow of PyTorch, they managed to provide an interface, an API, a programming interface, which is relatively good and relatively easy to use, and doesn't require much change in the code to move like from a sequential example to a parallel example, or just to use a GPU. And I think that what allowed most of the people to make this jump from, let's say, a laptop to a workstation with a GPU, and then going to multiple GPU, and then so they can make this job without thinking and going into the technical details.
I see. And very charged, very charged question. Do you think that this is the end of the CPU, or is the CPU going to have a comeback? Because linked to AI, there is definitely an optimized version on GPU performance and TPUs sometimes, but the TPUs didn't get that much in fashion as the GPUs yet, or will never. But the CPU is always the one that lags a little bit behind. Do you think it's the end, this big renaissance of HPC due to AI is the end of the CPU, or is the CPU going to make a comeback?
No, I think we still need the CPU of, I don't know, here, are you talking specifically about HPC, but for general computing, for sure, we still need CPUs. The applications are so different, and for some, it doesn't make sense to use a GPU. And actually, probably in terms of power consumption, it's better to have a CPU which is very versatile, can, shut off to save energy and things like that. And in the end, I think the architecture we see now on the supercomputer is this kind of hybrid platform where you have, let's say, one CPU. It's still relatively powerful, but with a couple of accelerators. And that's the thing, like you still need the CPU to drive the accelerators, the GPU in most of the case. So I don't see, let's say, in the next couple of years change that. Of course, the accelerator will get better. Maybe the CPU will adapt, but
And recently, Enrico, a friend we are doing the series on the physics informed neural network, shared me one link from Mozilla, and they are working on these llama files, that is basically large language models meant to run on a CPU to kind of give back. I don't know a lot about it. I just started looking at the technology, but it looks pretty interesting. So if you have a lot of CPU and you're in love with that, maybe that's a kind of project to look at. Very good. Yes. Xavier, thank you so much for today. And I think we already talked about 40 minutes. So I think we can call it a first episode, but we definitely have way more to discuss. So hopefully see you here again soon and explore a little bit more of the wonderful world of HPC.
That would be a pleasure. Thank you.